Now, there's another way to remove the image instead of filtering. And what we do is we notice that if the desired signal is down converted to omega IF, its image is converted to minus omega IF. And what we notice here is this signal is down converted here and the image is converted here. But as we saw before, the problem is that there is an image that's converted and dumps on top of our signal. So we'd like to somehow remove this image if we could. And last time we talked about doing that with filtering. Well, what if we took an idea similar to the Hartley single sideband? Remember that, where we used a 90-degree phase shift and a sine and cosine down conversion in order to basically generate spectrum that has one part is negative, one part's positive, and if you sum those up, they would cancel, whereas the other parts would superpose and give you twice the signal. And this is exactly how an image rejection works. We look at how the signal and its image are down converted, and what we do is we note that if we multiply the signals by cosine, and so what I have on here is two signals. I have the signal we want, and I have its image in red. And we multiply it by cosine omega t, and this is what we get on the output. Likewise, I can take the signal and its image, multiply it by sine omega t, and this is what I get on the output. And what we notice here is that the signals that are down converted by a cosine have the same sign, but when we mix with the sine, the signals have opposite signs. And now what we do is the same trick we did in the Hartley. We're going to add a 90-degree phase shift, and what that does is it creates the two original signals to have the same size, but the two images to have opposite sides. And the reason this is because the image that comes down on top of our signal is coming from the negative frequency. So remember, if we're down converting and here's our desired signal, it's the image up here that's getting down converted. So it's at the negative frequencies. And because of that, we're able to use this 90-degree shift in the sine to give us a negative answer. And you can see right away that these two are just going to cancel one another, and we're going to end up with a superposition of the two signals. And so that's just like the Hartley did for single sideband. But in that case, we were trying to eliminate a sideband. Here, we're just trying to eliminate an image. And so the complete image reject receiver looks almost just like a Hartley single sideband, but reversed, where we've got an LO creating a sine and a cosine. We've got a 90-degree phase shift. And you've noticed we've removed our image reject filter, and we can choose a very low IF to use that low absolute bandwidth of the signal. So it seems like if this works perfectly, we solved all of our problems. But there's a few problems, namely that the amplitude of the sine and the phase of the sine generally is going to have some error. And even if we made a 90-degree phase shift perfectly for one frequency, typically we can't make a perfect 90-degree phase shift for a range of frequencies. So there's always going to be some error here. So in practice, the two signals will have a different amplitude and phase error, the two LOs. The phase shift's not perfectly 90. And the two mixers, filters, and the combiner may also have mismatches here. So we've got a highly complex system that is going to have errors in several different places. So if we show all of the amplitude and phase mismatches with the parameters epsilon and delta theta respectively, we can actually write the image rejection ratio as the following. And this is just a derivation if you went through the math that you could use our previous equation for the IRR before. And if we assume that the amplitude mismatch and the phase mismatch are much smaller, we can simplify this into a nice handy equation where we can see that the ratio gets reduced by an increase in either of these parameters squared. So let's just look at an example. If an image reject receiver has a 10% amplitude error and a 10 degrees phase error, if there's a signal at the image frequency with 10 dB lower power than the desired channel, how much will the signal to interference ratio be at IF? Sounds like a lot of words, but we have all the pieces we need. So we can use our trusty equation. And I'm just going to note here that this is in radians, right? So this was in degrees, and now we're converting it into radians. And so what we find with this error is that we end up with a rejection ratio of 20 dB because we've got our 10% error and our 10 degrees of phase shift.